Good morning to everyone. My name is Teik Guan, and the title of my presentation is Calibrating LPN or Learning Parity with Noise Authentication for Low Resource Devices. This work is done in SUTD, Singapore University of Technology and Design, with my co-authors, Professor Zhou and Professor Jianying, both of whom are in the audience today. I have since graduated from SUTD and founded a startup called PQC focused on post-quantum security solutions. This work is partially supported by the Ministry of Education Singapore and also A-STAR under its RIE 2020 AME Industry Alignment Fund. The computational work performed in this research was partially run on resources of the National Supercomputing Centre, Singapore. The presentation will be broken into 4 parts. Besides the background and conclusion, we will cover 2 broad calibration aspects of LPN. The precision of authentication, which covers the false acceptance rates and false rejection rates, and the security of the key, which covers the key recovery by an attacker. Let's start with some background. LPN works on 2-dimensional matrices and 1-dimensional vectors in a binary base. It has its roots in code-based cryptography and can be seen as a simplified version of lattice-based cryptography, which is currently being standardized by NIST as part of its post-quantum cryptography program. I have provided a very simple example of a 3x3 matrix A and a 3x1 vector S. By doing a dot product of A dot S will yield B. A here is the challenge and B is the response, while S is the secret key. If given A and B, by Gaussian elimination, we can find the value of S. However, if we add a noise vector E to the dot product of A dot S to get B, then by Gaussian elimination, we do not get the correct result. In fact, it is a wrong S that will be obtained. This is the principle behind LPN. The experiments conducted in this research uses Hopper-Blum or HB protocol. HB is a challenge response authentication protocol designed over a vanilla LPN crypto system. Even with a simple protocol, you will notice that LPN already has a number of configuration parameters that has to be determined. Both prover and verifier share a secret key. This secret key is a binary vector whose size or key length k needs to be determined. There is a challenge A, which is a n by k binary matrix that is sent by the verifier to the prover. Number of columns on A is k, but we also need to decide the number of rows or the number of samples, n. The lower the number of samples will allow an attacker to guess a response at a higher probability, while a higher number of samples increase the communication overhead. Next, we need to decide a noise value tau, which is the probability between 0 to 0.5. A noise value of 0 is insecure as the secret key will then be solvable using Gaussian elimination, while a higher noise value increases the chance of attacker guessing right. In the diagram, the prover uses tau to generate an error vector E whose elements are 1 with probability tau. Finally, we have the authentication window delta used by the verifier. Since the error vector E is not sent from the prover, the verifier has to use tau to calculate the allowed number of errors, which is essentially the Hamming weight between the dot product without noise and the dot product with noise, and then provide for an additional delta in case of any false rejections. So compared to other crypto systems, which may only require the decision of a key length, the LPN system requires a minimum of 4 parameters: key length k, number of samples n, noise rate tau, and authentication window delta. Looking at the figure on the right, the HB protocol starts by the verifier sending a challenge A, a random n by k binary matrix to the prover. The prover generates the error vector E using noise rate tau. The prover computes B equal to the dot product of A and secret vector S prime and XORs it with E. Prover then sends the response B back to the verifier. Verifier computes its own dot product A dot with the secret vector S, XORs it with the response B, and gets the Hamming weight. If the Hamming weight is within an acceptable value, which is directly proportional to the number of samples N and noise rate tau, then the authentication is okay. So HB is secure only if challenge A cannot be manipulated by an active attacker. There are many subsequent proposals to HB to address this weakness, such as HB+, HB++, HB hex, but we are working on HB in this paper as it is the common denominator. From a low resource view, we assume the use of ISO 18000-6 specifications and with an authentication cycle of up to 1 second. Under the UHF RFID standard, it determines a 40,000 kilobit per second as the transmission bandwidth, which translates to about a sample size of 500 with key size of about 80 bits. We noticed that many RFID brands popularly made have a lifetime of 100,000 cycles. So let's start with the precision of authentication. The question we hope to answer is to help determine what are the appropriate values of K, the key size, N, the sample size, tau, the noise rate, and delta, the authentication window, to keep the precision of authentication good. We measure precision based on two values, FAR and FRR. Both these values should be as low as possible. False acceptance rate, or FAR, refers to the probability that the verifier would accept the authentication response B from a prover who doesn't know the secret key S. This is the authentication security as we know it. False rejection rate, or FRR, refers to the probability that the verifier would reject the authentication response B from a prover using the correct secret key. This affects the usability of the system. When looking at statistical bounds, past work include Levi and Fong's Stirling formula and Kubler's Chernoff bounds to determine the bounds at which FAR and FRR will sit. We plotted them using FAR, FRR on the y-axis and the authentication window delta on the x-axis as shown in the figures, using sample size of n equals to 500. The solid lines refer to a noise rate of 0.125, while the dotted lines refer to a noise rate of 0.4. When looking at the delta between 0 and 1, we notice that much of the graph has error rates above 0. Both papers suggest higher sample rates and in order to reduce the errors, but this breaks the low resource assumption that LPN is supposed to provide. So instead, we designed and carried out experiment 1, which ran 1,000 simulations between the prover and verifier, and we varied the 4 parameters: sample size from 50 to 900, key size from 100 to 500, noise rate from 0.01 to 0.49, and delta from 0.0 to 1.0, all in small steps. We arrived at some colorful graphs which I will run through in my subsequent slides and provide you some findings. Let's start with FAR. The y-axis is the FAR error, and we want this graph to be as close to 0 as possible. When reading the x-axis, it is increasing in noise rate from 0.01 on the left to 0.49 on the right. From the graph, we notice that FAR is good for noise rates at 0.125 and below, regardless of sample size and delta. Within each noise band, we have increasing sample sizes from 50 to 900, where we can see FAR improves to 0 as the number of samples increase. The different colors represent the authentication window delta used by the verifier, where maroon starts at 0.0, followed by red at 0.1, orange 0.2, all the way to purple at 0.9 and gray at 1.0. Smaller deltas means that the prover cannot easily guess the secret key, while larger deltas are totally insecure as the verifier can accept any response. The bundling of different lines within the colors, the solid, the dashed, the dotted, refer to the different key sizes used. Looking at FRR, The y-axis again is the FRR rate, where we want it to be as close to 0. First of all, there are no obvious noise values that will definitely give us a good FRR. Next, increasing noise rates, authentication window, and sample sizes seem to give better outcomes, which is the opposite picture to FAR. So let's superimpose the two graphs so that we can get a complete picture. We summarize what we see in the 5 observations, but I'm sure we can get more. 1. Key lengths do not affect FAR, FRR. 2. Low FAR is easy to reach for noise rates at 0.125 and below. For higher noise rates, we need smaller delta and larger sample sizes. 3. For noise rates above 0.4, we cannot find low FAR with practical sample sizes. 4. The authentication window delta cannot be 0, as FRR is 50% regardless of the other parameters. And for 5, for low FRRs, we need a higher noise rate, higher sample sizes, and larger deltas. So can we find good parameter values? We extracted combinations of noise rate, sample sizes, and delta where FAR and FRR are 0 for all 1,000 simulations. We chose only combinations that pass both the FAR and FRR. We then cross-checked it against Stirling formula and Chernoff bounds, and removed any that exceed the bounds of 2 to the power of minus 40. We then arrive at the value shown here. Only the noise rates of 0.05 and 0.125 are recommended, and for some of the sample sizes used, we have provided appropriate values of delta which can be used to achieve low FAR and FRR. In the next part of our experiment, we now try to understand more about the key size. Since smaller key sizes are susceptible to brute force and other effects, while larger key sizes affect the computational and transmission overheads, we ask if there's a balance that can be reached. We notice that past literature do not have any assumption on the total number of samples, which is the number of samples per cycle multiplied by the total number of cycles, or the total lifetime of a key. And we ask if limiting this can help keep key sizes small. We take direction from Lentra and Verhoeven's paper, Selecting Cryptographic Key Sizes in Our Approach. It lists the different aspects that needs to be considered, and we examine that in our paper. First, the key length recommendation is 64 bits for retail, a bit small for today's standards. And we note that a number of RFID implementations already support an 80-bit key. Next, what is the effectiveness of known attacks? For LPN, it will be the Blum, Carlyle, Wasserman's, or BKW. We designed experiment 2 to apply BKW for a limited number of total samples of 50 million. 50 million is essentially computed by assuming a 500 size sample per cycle multiplied over 100,000 cycles. Since BKW works similarly to Gaussian elimination but reduces cumulative errors by grouping partial sequences, we run our experiment by seeing how effective BKW can be to find blocks of partial sequences for different key lengths over a 50 million sample size. We vary the number of samples from 10 to 50 million, use different noise rates, and slowly increase the key sizes from 16 upwards. From our experiment, a maximum key size of 52 was the limit where BKW could effectively group the partial sequences for the sample size of 50 million total samples. Then, what is the effectiveness of key guessing? Instead of randomly guessing, we employ the use of machine learning to help us here. We use extremely randomized keys, an ensemble learning technique demonstrated by Kubler in his online blog. ERT makes sense since it learns using a subset of features instead of all features, which allows some of the noise to be possibly excluded. We vary the number of samples from 1,000 to 50 million, use different noise rates, and slowly increase the key sizes. As expected, ERT performs better in low noise rates and struggles when noise rates get higher. However, for 50 million samples, ERT cannot guess beyond k equals 24. Following on, what is the effectiveness of incomplete attacks? By this, we interpret it as being able to guess some parts of the secret key correctly. We use genetic algorithm, another machine learning technique, to explore if this can be achieved, since GA works on the principle of mutating different possible answers in an attempt to get closer to the optimal one. In this experiment, the total number of samples is not relevant, but the number of generations that GA is allowed to mutate matters. Given 500 samples on a 4-mating parent with a mutation percentage of 10%, we ran GA across 10 million generations and really could not achieve a key recovery beyond k equals to 28. When comparing with a typical brute force guessing, look at the blue line, GA seems to perform poorly in larger key sizes. We suspect this is due to repetitions in mutated solutions as the key sizes went up. Finally, for brute force attack, we did a back-of-the-envelope calculation assuming that an attacker has a 10,000 node supercomputer running at 3 GHz each, and each LPN computation takes up 1 cycle. For k equals to 64, it would take the attacker somewhere around 4 years, while for k equals 90, it stretches to several millennia. So we summarize the findings in the table shown. And even with a 50% buffer for computational and algorithmic improvements, we think that k equals 64 is usable for up to a year or 1,000 cycles, while k equals 80 is usable for 5 years or 100,000 cycles. In conclusion, we think that LPN is an important cryptosystem for low-resource devices, and finding appropriate parameters such as sample size, noise rates, authentication window will help its adoption. We also find that limiting the total number of samples can help manage the key sizes into a much more smaller and usable form. This work was run on the NSCC computers with over 70,000 node hours consumed. Future work include applying these values on the derived HB protocols and using a usability study on real-life RFID system. We also think that LPN can form the basis for a low-resource post-quantum authentication algorithm. We are happy to collaborate. I have placed contact details of Professor Zhou and Professor Jianying, who are currently still in SUTD, as well as myself in my startup PQC. Thank you.